guess, but maybe not trivial. There was that problem later on. Which one was the curvature one? I didn't even know. Oh, the last one was the curvature one. So the one before it, it's something like this. If you want to find the length of a vector and it only has one component, what is the length of the vector? So if you have that vector, what's the magnitude of that vector? 2, right? So we take the absolute value of the only non-zero component. So what about if you have something like this? So if you have another situation where, let's suppose we had 0, 0, and then we had 4 minus 4 cosine theta, or t, or whatever, like that. What's the magnitude of that?
4 minus 4 cosine t.
So the magnitude of this is the absolute value of this.
But that never becomes negative.
This never becomes negative, so it's no problem. No problem. But in contrast to this. How about in contrast to that? Absolute value of this vector, the magnitude of this vector. Okay, so here's where we have a momentary pause. You can either leave the absolute values, and I would have accepted that. But can anyone, first off, does everyone agree that that can be negative? And if you plug in 0 for t, cosine of 0, oh, maybe that's not a good number. What about pi over 2? Plug in pi over 2, cosine of pi over 2 is 0, 0 minus 4 is negative 4. So definitely that can be negative. How can we force that to be positive without the absolute value bars, but not goof up the magnitude? Can we just do that? Then we're going to have the same magnitude for all t values, and it will always be positive. So that takes care of the absolute value bar all at once if we just switch the two. Everyone agree? Do you need proof? 1/2 minus 1 is negative 1/2, which has a magnitude of 1/2. But 1 minus 1/2 is positive 1/2, which has the same magnitude. So the magnitude of a minus b and b minus a are the same. Correct? A minus b and b minus a have the same magnitude. So if a minus b could be negative, and you're looking for the absolute value, then just swap them, and you get b minus a. Okay, a couple other things. If you haven't read the grading guidelines yet, you should read those, because I grade differently than others. So every problem is out of 5. And then I grade it more like a GPA type of thing. Add up all the points that you got, divide by the total number of problems on the test. That gives me a number between 0 and 5. And if you look in the grading guidelines, you will see a little chart of what's going on over there. Clumsiness is fine. Whoops, I got distracted there. So 100%, 90%, 3 corresponds to 80%, 2.5 corresponds to 70%, and 2 corresponds to 60%, and 1 corresponds to 50%. So there's a little table in the grading guidelines. It's very GPA-ish type thing, and that's how your percentage is arrived at by going back and using this conversion. So if you ended up with a 3.5 average, you ended up with an 85% on the test. So some people like to think of it as a built-in curve, because on a 10-question test where every question is weighted equally, 8 out of 10 gives you 90% instead of 80%. So in that sense, there's a built-in curve. But in classes like Calc 3, there's really no easy questions. Like in algebra classes, a lot of teachers will throw on a bunch of easy questions to sort of balance it out. Calc 3, though, most of the questions are pretty, they're kind of hard. So this is, I think, a more fair way to build it in. And then when I take points off, I try to take them off in a very systematic way where I take 2 points off for any conceptual error and 1 point off for any trivial error. So I was kind of lenient on the first test. I'm always a little bit lenient with some of the trivial errors. On the future tests, I'll be more strict. And every time there's a trivial error, I'll take off a point. If you don't reduce, there's no reason in a class like this that you should be leaving something like that. I saw a couple of things where things were not reduced. Something like that. If the expectation is that you reduce all your fractions, you simplify all your square roots. If you have a square root of 50, the expectation is that you know how to solve this and rewrite this as 5 root 2. So future tests, I'll definitely be more strict about that. Always point off for units. If a problem has units and you didn't put the units, then you lose points. What other common things are there? I don't know. I can't think of any other ones. Any questions that you can think of? So make sure that I added your points up right. Make sure I graded make sure I graded what you wanted me to grade, in other words. Add up the points, make sure they're right. Make sure I divided by, what do we have, 15 questions? Make sure I divided by 15 correctly. All that stuff. Just in case. Just in case. Any other questions before we go on? Is there a question on here you want me to at least verbally tell you how to do? Or? Let me do one question, because this was the one that was missed most often. A lot of folks got partial credit on it, but did not. There was probably only 5 or 6 that got full credit on it, and that was number 9. So we had, and this is a good one to kind of analyze in a little detail because it gets at a couple of different concepts that should be understood well before moving on. And I think that's the right function. Does that look good? We had that T naught was 0, I think. Okay, so this is just a curve in 3-dimensional space. Curve in 3 space. You should just be visualizing some wiggling curve in 3-dimensional space. We know it's in 3 space because there's 3 components. We know it's a curve because there's only one parameter, t. When we get to surfaces, we're going to have 2 parameters. We'll have a u and a v, sometimes an s and a t. When we take the derivative here, we get the velocity vector. So you should be envisioning a vector that's tangent to the curve here. So we have 1 plus 3t to the half, so it's 1/2 that quantity to the negative 1/2, so we get that. Derivative of the middle term, we have to use the quotient rule. You can think of it as t minus 1 to the negative 1 if you want. However, you use your quotient rule or do your derivatives. Whoops, should that be, what should the power be? Squared. Derivative of cosine of sine, negative sine of the same angle. But then we have to multiply by the derivative of the angle.
I think your first one, there should be a 3 on the top.
Yeah.
Times 3, thank you, I didn't chain rule it. Did not chain rule it. Multiply by 3, thanks. Okay, so those are our derivatives. Now that is not a line. That is not a line. That is not linear. Definitely not a line. Its absolute value, well, let's not do that. That sounds horrible. Let's evaluate it at our point of interest. Point of interest is when t is 0. So we plug in t equals 0, and we end up with that. That is not a line. Not a line. We have talked about lines so much, and we know that a line has the form of r naught plus t times the direction vector v. There's no way it's a line without a t in it, right? You need to get all the points on the line. This is a constant vector that points to a single point in three-dimensional space. A single point is not a line. We need an infinite number of points with this direction. So this is our direction vector. Bless you. And so that's what goes in here for V, right there. And then how about our starting vector? What do we use for our origin or the beginning of this line?
R of 0.
R of 0. R of 0 is what we will use to be R naught. That's going to be our so-called origin. So plug that in, and we get 1, negative 1, 1. So that's our starting point. 1, negative 1, 1. So we go 1, negative 1, 1, plus t times this direction. So that is our line. I know that my math lab doesn't always want you to combine, but most books, most mathematicians want this combined into one vector. So that would be your line. So anytime you're trying to find the equation of a line, you need two pieces of information: direction vector and starting point. Those are the two things. Any questions on that? All right, let's go ahead and do some math. Wait, 12.1? What the heck? We already did that. Now I gotta figure out how to save those other notes. We're in 12.3. All right, 12.3.
Did we finish
Oh.
12.2?
I believe we did.
Yes, we did.
Yeah, I believe we finished 12.2.
Because then you
Saba,
get
you had a question on 12.1 homework, though. Let's pull that up and talk about. First one was number 5, I think. Let's talk for a second about the
yes,
homework.
Let's do number 5.
Let's talk about number 5, and you do number 5. So this question here, so good question. Let's try to understand it. We have two planes right here, and they intersect, and we want to find the equation of the line. So we've got this plane and this plane. We're trying to find the equation of that line right there. So we need two things: direction vector and starting point. Well, if we want to have the line right there, the way we get the direction vector is to take the normal from plane 1, the normal from plane 2, and cross them. So we're going to crisscross the two normals. So the normal from plane 1 is 1, negative 2, 3. The normal for plane 2 is 1, 1, 1. So if we cross those, that gives us the normal, or gives us the direction for the line. So normal vector crossed with normal vector gives us direction vector for that line. Any question on that? Everyone see how two vectors being crossed will give us the direction of the line? Right. And then we have to find a point, a starting point. So we need one point that is on both those, we need one point that is on both those planes. It's on the intersection. So to find a point that's on the intersection, we have a couple of ways to do it. The standard way is to do a system. Put this plane right below that plane, add or subtract so that you eliminate x or y or z, and then you have a two-variable equation, and then you just plug, if you solve for z in terms of y, plug in y equals 0, figure out what z has to be, and then back up and get x, and that will give you your starting point. All right? Simultaneously solve to get your common point. So any questions on either of those two steps? Direction is found by crossing the two normals. One start point is found by eliminating x, solving for z in terms of y, plug in y equals 0, get your z, back substitute to get x. Make sense? Saba?
Yes, thank you.
And then 7, I think you also had a question on. Is that right? Is it 7? I think it was 7. So this says, determine whether the following statements are true or false. This is a great question. There's like 8 parts, and every part is very conceptual. This is a really good question to go through very carefully, because if you don't get each one of the parts on this question, you definitely have a conceptual hole. A hole. So really important one. So let's talk about maybe a couple of these 8 parts. So the first thing says a plane passing through this point with a normal vector there is the same as the plane passing through that point with that normal vector. Well, one thing we would know for sure is if the planes are going to coincide, if they're going to be identical, the normal vectors have to be scalar multiples of each other. Right, so if we build this plane here, we do n multiplied by the displacement vector off of 1, 1, 1. That displacement vector is x minus 1, y minus 1, z minus 1. Dot with that has to be 0. So that builds a plane. The plane that this one builds, same idea. N dot v is 0. So there's n. V, x minus 3, y minus 0, z minus 1. That's the displacement vector in the plane pivoting off that point. Get that equation. They have to be the same if they're going to be the same plane. They've got to be identical. So one of the conditions, when we look at this, we see, oh yeah, this normal vector is minus 2 times that one. So there's a chance that they're the same plane. But the only way to know for sure is if you build each plane's equation, and if they're the same, then the planes are identical. Everyone follow the logic there? So a plane has an infinite number of points. So this point here and that point both being on the, there's no way we can test just by knowing a random point on each plane. We have to actually look at both equations and see if they're the same.
Why is the normal vector not enough to determine?
Because they could be parallel planes.
Right.
So if the normal vectors are parallel, then you have parallel planes. But if you want the planes to actually coincide,
Gotcha.
then you have to test that that the equations are the same.
Okay.
One other possibility conceptually is that one thing you're thinking of is that 1, 1, 1 is on this plane and 3, 0, 1 is on that plane. If you can kind of think of it that way also.
Okay.
But the simplest way is to build the plane equation, simplify both. They have to be the same. And if they're not the same, then the answer is false.
And this one is false, right?
I don't remember. And it may be different for different people.
Well, based off what we have here, we got 1 and 1, and we got 3 and 2 for the x values.
Well, the normal vectors are fine.
But the positioning vectors are not.
We can't tell just by looking at those points. We would have to, maybe you're doing the math in your head, but so you have to do x minus 1 times 1, y minus 1 times 2, z minus 1 times that.
Yeah, you get x minus 1, then you get.
So 1 plus 2 is 3. You get 0. You get 0, and here you get negative 6.
Yeah.
Plus, they're the same plane here.
Well, can you tell
Same
that
plane.
by the fact that there's a 1 in both z coordinates for the points?
No, because if you take a plane, there's going to be an infinite number of points that have a z value of 1. Right? On any given plane, you're going to be able to intersect it with the plane z equals 1, and you're going to have a line in it also. If you've got some tilted plane, there's an infinite number of points that have a z value of 1. Infinite number of points that have a y value of 1. Infinite number of points that have an x value of 1. If the plane is tilted and it's not parallel to a coordinate plane. So that's not enough to tell. Yeah, so if you write out the 2 planar equations, you will see it crystal clear. Oh, and actually we were going to go and do at least one more of those. So what did we say? This is going to be true. So let's look at this one. So there we have 2 plane equations. Question says, are they the same plane?
No.
Okay, so the normal vector for this plane, 1, 1, negative 1. Normal vector for this one is just the opposite of it, negative 1, negative 1, 1.
So they're parallel.
So if we wanted to multiply this one by negative 1, we would have the same left side but different right sides, so that would mean that we have parallel planes. Exactly. Because they have the same equation, the left side is the same, but the right side is different. One's plus 1, one's minus 1. But the planes are not 2 units apart. Not 2 units apart. All right, so this one, this will be the last one we do from this group, I think. So this one says, given a plane Q, there is exactly one plane orthogonal to Q. True or false? False. So if you're given a plane, there it is. There are an infinite number of orthogonal planes. Correct?
That just means perpendicular.
Yes. Orthogonal and perpendicular are essentially the same. Usually in math, orthogonal is referring to vectors and geometric objects, and usually in perpendicular is usually just referring to lines. But usually orthogonal seems to imply vectors. These days, they're interchangeable. Yeah, so go through that one carefully, because it really, getting those conceptual ideas down is very helpful to organize all the thoughts on how this material interacts with itself. 11. So this one says, find the points, if they exist, at which the plane and the curve intersect. So we've got a plane in 3-dimensional space, we've got a curve in 3-dimensional space, and if the plane and the curve intersect, they have to intersect at a t or t value, one or more t values. So if we want to figure out where two geometric objects intersect, we plug one into the other. This tells us that all the points on the curve R have x equal to t, y equal to t squared, and z equal to 2t squared. So if we take the line and we take its components and plug them in for x, y, and z, that gives us an equation with just a t in it. Solve for t. Once we get our t value or values, we would plug them back into the line or the curve to figure out where on the curve those intersection points are. That makes sense to everyone? So take the t values, plug them into the plane, solve for t, plug back into the curve to get the actual ordered triples for the intersection points. Make sense?
Yes.
Okay. All right, and so that's kind of true with lots of different systems. You're going to plug one into the other and then figure out what's going on. And, in this case, in some ways, it's simpler because you're replacing the x, the y, and the z all with expressions of t, so you only have one variable. So in a lot of ways, solving, when you're dealing with that other problem where you have two planes and you're finding the line of intersection, it's harder to find that common point. That's more work, finding that common point, because you've got to eliminate x, plug in a y, find z, back substitute. That's more complicated. All right, well, let's carry on. Carry on. All right, so we get to deal with some abstract ideas today. Abstract ideas. Looks very technical up there, because it is. All right, so first let's revisit the idea of limit. So you have all done the limit of a one variable function, and you use the limits for several different purposes. One important purpose was to define continuity. So we know that a function is continuous at a point. First off, when we think about continuity, it's a point-wise concept. So if we have some curve like this, that's in a coordinate plane. If we have something like that, the idea is that you're looking at it point by point. Is it continuous at A? Is it continuous at B? Is it continuous at C? Is it continuous at D? So you're sort of scanning across. For a function to be continuous, it's got to be continuous everywhere on its domain. Obviously, that function's not continuous. And the idea behind continuity is that the limit and the value of the function are the same. That's what it means for a function to be continuous. So right here, if we call that point C, the value of the function at C is whatever that number is right there. So f of C is whatever this number is over here. Let's just call it D. But the limit of the function as x approaches C is whatever is up here. Let's call it E. So those are not equal. So therefore, the function is not continuous. For a function to be continuous, the limit and the value must be the same. So any questions on that Calc 1 idea? So the limit, we say that the limit of this function, oh, and I forgot I said one thing incorrectly here. The limit of the function here, we learned in Calc 1 that when for the limit at C to exist, there has to be the right limit and the left limit have to both be equal. So I should be talking, because this is different, we have a gap, we should be talking about one-sided limits. So let me add one other piece. The example I should have put up here is slightly different for this, but this works totally fine. So as we approach x, as x approaches C, from the right-hand side we get E, and the limit of f as we approach C from the left-hand side is D, and D is not equal to E, so the limit does not exist, so the function's not continuous. So a function cannot be continuous in two different ways. The limit doesn't exist at all. If the limit doesn't exist, then there's no way it's continuous like this. Or the other case, which was the case I kind of had in my mind at first. So this situation. Here, the limit does exist, but it's not equal to the function. So again, let's call that D. Let's call that E. So the limit of the function here is D. The value of the function here is E, the way I've written this one. So that's our C value right down there. And so here, D is not equal to E. So in both those cases, the function is not continuous. In the top one, it's not continuous because the limit doesn't even exist. And in the bottom one, it's not continuous because the limit and the value are different. So limit and value are different. So that's one of the main things that we think of with limits. We think of continuity. And now that's a one variable case. So now let's analyze this statement here. This is a two variable idea here for a limit. And so we are going to say that the limit of f, we can write it in two different ways. We can talk about it as ordered pairs, where x, y goes to a, b, or you can just label them as points. You can think of the limit at p, as p goes to p sub 0, you can do it either of those ways, is totally fine, is L. So for that to be true, we just talked briefly up here with a one variable function, there's only two ways to approach C. You're either coming in from the right or you're coming in from the left. So up here we can say the limit exists if the right limit's the same as the left limit. When we're in two-dimensional space, when we're approaching P naught, there is a bazillion ways that you can approach P naught from P. There are lots of paths that you can take. And so it becomes a much more, it's a vast question. Is it continuous? Is a two-variable function continuous at a point? And it's impossible to do what we just did up there, where with a one-variable case, you can come in from the left, you can come in from the right. If they're equal, the limit exists. With the two-variable case, there's an infinite number of ways to get to P naught. You cannot test them all. It's impossible to test every single path. So we have to use some broader concepts in order to decide whether a function is continuous or not. We can't just do that simple test, left limit, right limit. Oh, they're the same, therefore the limit exists. We can't do that here. So for a two-variable function to have a limit that exists, it doesn't matter how you get to P naught, you must have the same exact limit for every single path to P naught. Now, this idea does allow us to decide when a limit doesn't exist. If we can find two paths to P naught that have different limiting values, then we know the limit does not exist. Just like up here, we come in from the left, we come in from the right, we get two different limiting values. That means the overall limit does not exist. So with a two-variable function, if we can find two different paths with two different limits, then we know the overall limit does not exist. Every path has to have the same limiting value for the overall limit to exist. Okay, so back in Calc 1, you dealt a lot with this x minus a's magnitude is small. And so this is the notation that we use in one variable calculus. We say the absolute value of x minus a is small. All we mean is that a is that we're within delta units of a, that x is within delta of a. So it's just a neighborhood. We use the word neighborhood a lot when we start getting up here in Calc 3. This highlighted segment is a neighborhood of a. And so for x to be in a neighborhood of a, that just means that x minus a is small. The magnitude of x minus a is small. So we have to translate that to two variables. Well, what does it mean for us to be close or for the distance to P naught to be small? Well, we know how to use the distance formula, and the idea is that we, instead of creating an interval around A, so that's our point of interest, instead of creating an interval, a delta interval, we create a delta disk. So to be close to P naught, you have to be within delta of P naught. So you have to be in this neighborhood of P naught. Up here, your neighborhood is one-dimensional. Down here, your neighborhood is two-dimensional. It just means that you're within delta of A, or P sub 0 here. So up here, within delta means interval. Down here, within delta means disk. Right? Pretty straightforward. If you're going to be within delta of a point in three-dimensional space, what should we be thinking? Sphere. Yeah, little ball. So then we would have x minus a squared, y minus b squared, z minus c squared, all less than delta. Yeah, so, etc. So this idea here is the idea of a neighborhood. Being in the neighborhood of a point just means being close to the point. Okay. So here is the formal definition of a limit. So the function f has a limit L. Again, you can write it either with ordered pair notation or point name, either with the names of the points, either way. So for the limit to exist, and be L, that means that given any epsilon greater than 0, there's a delta greater than 0 such that that difference is true whenever x and y in the domain and we are close to P naught. So let's analyze this for a second. We're not going to do a ton of work with the details of this, but let's try to figure out what it means. So first off, this limit here is a number. That's a number that we think of as on the z-axis because we're dealing with a surface. The domain is in the xy plane. The z values or function values are coming off the z-axis. The limit, if the surface has a limit, if you imagine a surface with a relative max up there, that limit is going to be a z value. And so this says that the function value minus the limit is small. Right, so f minus L is small. That just means that the z difference is small. If you're looking on the z-axis, the function value is on the z-axis. L is just a number on the z-axis, and this just says that if we get, when these are super close together, the corresponding x's or the corresponding points in the domain are super close together. That's what that's saying.
So what's the definition of small?
That small means that the point in question is within delta of your target point.
Okay.
So that's what this is right here. So you can think of it in one-dimensional or two-dimensional. So here, x and a, the difference between them is small, means that their difference is less than delta.
So are we gonna be having a delta value that we're working off of, or we have to figure out?
We're going to do it just conceptually, because in one-dimensional calculus, you can say, hey, what is delta? And you can figure out what the delta is. Here, we cannot figure out what the delta is. It's too complicated. So we won't do that here. But the concept is the idea. Let's think about it from the one variable case for a second, because that is it's much easier to understand conceptually. And actually, in our book, there's some interactive figures that have some actually good limit types of, what are they called, simulations. So the idea here, if we want to test whether the function has a limit at c, the idea is that we suspect that the limit is right there. We suspect that it's L. And the idea with epsilon is that for every epsilon, so there's L plus epsilon, there's L minus epsilon, it's going to be continuous. It's going to have a limit if no matter how small you pick that epsilon, you are going to be able to find a corresponding delta. So if we build this so-called epsilon interval here, we go over to the function, and that corresponds to a delta interval. So then we look and we figure out what the delta interval is. So that's c plus delta, this is c minus delta. So if this is true, if you can always find a delta, no matter how tight you build that little epsilon band here, no matter how small this is, if it's true for every single epsilon greater than 0, if no matter how small you make this epsilon band, you can always find a delta, then the limit exists. The limit is not going to exist if you have a gap. So if we have this situation here, we suspect that our limit is the value of the function. That's what we always suspect, that the limit's the value of the function. And notice here that if I get epsilon too small, well, when epsilon gets small, when it gets this small, right now, woo, that goes on forever, and there is no delta. So the limit won't exist if you can find epsilon that doesn't have a corresponding delta. The limit will exist, so it's kind of like this ratcheting thing. As you ratchet epsilon smaller, then delta clearly has to be smaller. And if there is no problem, no matter how small you pick that delta, there's always a corresponding no matter how small you pick epsilon, there's always a corresponding delta, then the limit exists. The limit won't exist when at some threshold your delta is so small, your epsilon is so small that there's no corresponding delta. So over here, we just have to think a little bit differently in 2 dimensions. So here's our delta interval in 1 dimension. Our delta interval, quote unquote, in 2 dimensions is a disk. So the idea then is that in 2 dimensions, no matter how close we let L and F get, so this is a point on the curve, on the surface, no matter how close they get, we're within epsilon, then we're going to have P, we're going to be able to build this, this delta disk around P naught. So as we get closer and closer to the L value with our function values, the disk is shrinking down below. And if, at some point, if there's a gap, there's going to be no delta that builds a disk.
Is that supposed to be like P times P naught, or is that supposed to be a vector?
That's this is
Like the absolute value of
this
the
is the magnitude of the vector from P to P naught.
Okay.
Yeah, so that's the distance from P to P naught.
It's just kind of hard to tell when they don't put the little arrow.
I know. They don't do what they should do. Yeah.
So on this graph, basically epsilon is just like a range, an interval along the y-axis. Does that mean epsilon is basically the disk itself, like the area of the disk, or what does it represent? Like
So epsilon is always measuring a distance on your dependent axis.
Okay, so it is just an interval on the z.
It's just an
Okay.
interval. So even in the 2-dimensional case, epsilon is representing an interval on the z-axis. So
Okay.
it's still, it plays the same exact role. Instead of an interval on the y-axis, it's an interval on the z-axis.
All right.
The thing that's different is that the delta interval on the x-axis for a one-variable case is an interval, whereas the delta, quote unquote, interval when you have a two-dimensional domain is really a disk. And then if you go to one level up, you could have an epsilon ball instead of an epsilon disk or an epsilon interval or whatever. I should say delta. You have a delta ball instead of a delta disk or a delta interval. Okay, so let's look at this limit here. So it says that, this just says that if the z values get arbitrarily close, if they get super close, if they get ridiculously close, there has to be a ridiculously small disk that contains the distance to the point that we're trying to find the limit at, p sub 0. So it just means that we're ridiculously close to p naught if we're ridiculously close to L. So as we're ratcheting closer to L, we're ratcheting closer to p naught. So it's just that kind of squeezing. Squeeze closer to your limit value. If there's a delta thing, whether it's an interval or a disk, there has to be one of those if there's going to be a limit.
So I just want to make sure I understand. The
Sure.
delta becomes a disk, but the epsilon remains a band.
Yes.
Like that's how I.
In two-dimensional space, it's almost more like planes.
Okay.
But it's still they're inner. So if you look at the top of your function, you sort of imagine the plane coming across and hitting the z-axis at one point, and you imagine some random point that's moving closer and closer to the point on the top there. So you can imagine two planes and they're intersecting the z-axis, but it is an interval for the epsilon always.
Okay.
It's always an interval of numbers, as opposed to a disk or an interval for delta. Okay, so this just says if you let epsilon get ridiculously close to 0, then there's going to be a corresponding delta disk, so that all the function values in that disk will fall within that epsilon interval on the z-axis. So very abstract. It's something we aren't going to use because it's impossible to find delta. In Calc 1, you can find delta. You can say let epsilon be greater than 0, and you can say, okay, let's let epsilon be 1/2. And then you can figure out the delta that works for 1/2. You cannot do that here. It's way more complicated. So it's the concept that we're interested in. Limit exists if you get close with epsilon, then you have to get close with delta. Okay, so nothing fancy here. Don't even write this down. This should be exactly what you think. The limit of a constant function is the constant, just like in Calc 1. Limit of 5, as x goes to wherever, is 5. Right? The limit of a constant is itself. Nothing complicated. The limit of a constant is itself, no matter what. Here, we're looking at ordered pairs. The limit of this function, so our function is just the function f equals x. The limit of that function as x, if we look down here and our x and y, we're going closer and closer to ab. Well, the limit of x as x goes to a is a. The limit of y as y goes to b is b. So those are the same ones, the same basic limits that you based everything off of in Calc 1. In Calc 1, it just looked a little bit different. You said the limit of c as x went to c is c. Oh my gosh. Is c. And you said the limit of x as x goes to whatever, a in this case, is a. Those were your two basic limits in Calc 1, and all other limits were based on those two. That's where you started. Those are the two basic limits that you can prove it using the epsilons and deltas in Calc 1 pretty easily. Here it wouldn't be that hard to prove these two. So all other limits are based on those two. So if you believe those two, then we can use bigger math to solve all the other ones, if you believe those two. Those two they usually prove, and then you go on with limit rules. Again, don't bother writing these down. It's totally intuitive. The limit of a sum is a sum of limits. If the limit of f is L, the limit of g is m, then the limit of f plus g has to be L plus m. Totally intuitive. The limit of a difference is a difference of limits. The limit of a constant times a function is the same constant multiplied by the limit of the function. So all of these are exactly what you would assume if somebody just put a gun to your head and said, what's the limit of f times g? You would say L times m, right? That's what you would assume. What's the limit of f over g? L over m. That's what you would assume. There's nothing that's unintuitive all the way through. If you have a function raised to a power, when you raise a function to a power, that's a continuous type of thing. So you can push the limit inside, and you can take the limit of f, and the limit of f is L, so the limit of the whole thing is L to the n. So you can do what you have always done in Calc 1. You've done all this, it's just now we have a two-variable function. Okay, same thing is true with the fractional exponent. Just take the limit of the base. You know, as long as the limit exists, you just take the limit of the function part, and then all the other stuff just comes along. You know, like if you have the limit of a square root, you just push the limit inside the square root, but the square root stays. You just take the limit of the x part, and everything else just comes along. So nothing mysterious. So let's prove to you that it's not mysterious. So the first thing you always do with limits is you plug in the values. Plug in the x values, plug in the y values, and if you get a number, you're done. That just means the function that you're analyzing is continuous at the point down here. So that's always the first thing you do. Okay, you plug it in, you just do this. And if you do this and you get a number, you're done. It's when we get indeterminate forms and things like that that we have to do a little bit more analysis. So there's our limit, as long as I did the algebra right. And that's what you did in Calc 1 too. You just plug it in, if you get a number, you're done. If you get 0 over 0, then you had to look more carefully. You had to analyze something that we called an indeterminate form.
All limits are going to be just like that one, right? Just that.
At their core, yes. How about this one? So here's a great example. So we have all this stuff attached to the function. If we look inside the letters, the variables, x and y, there's this square root symbol attached, there's this natural log symbol attached. We can always, we deal with continuous functions, and the limit symbol can always be pushed. I'll write it out this one time because it's so painful to write it out too much. So here I've pushed, and once we know the subscript on the limit, you don't have to rewrite it a million times. Especially, it gets really messy in two-variable calc, multivariable calc. If you're going to an ordered pair and ordered triple, to rewrite that every single time you write the word LIM is a pain in the neck. If you do it once though, so we know from here on, when we write LIM, we mean as xy goes to e squared comma 4. Rewriting that every time is unnecessary. But the natural log function is a continuous function. Limits can go through continuous functions, so we can push it through the ln function to the inside. Now we're on the inside. Well, same situation. The square root is a continuous function on its domain. So we can push it all the way in. You can always push that limit symbol all the way down until you're doing these two basic limits right there. You can always push it so that you're just getting down to that basic fact right there, those two basic facts. Every limit question boils down to those two basic facts. And so now we have ln of square root, the limit of x times y. All right, let's just do it all the way down. This is the limit of x times the limit of y. And now we're all the way boiled down to the basic facts. Limit of x as x goes to e squared, of course, is e squared. The limit of y as y goes to 4 is that. So this turns into the natural log of, let's see, the square root of e squared. That e is a positive number, so we don't have to deal with any absolute values. So we get the natural log of 2e. And then that is the natural log of 2, what? How do we?
Plus the natural log of e.
Plus the natural log of e. Using our log log rules. So we end up with natural log of 2 plus 1. So that'll be our limit, the limiting value of the function as xy goes to e squared comma 4.
Question?
Yeah.
So if you do get an indeterminate form, does L'Hopital's rule still work for this? Oh, cool.
No. No, L'Hopital's rule only works in one-dimensional space. I shouldn't say one-dimensional, two-dimensional space with one variable limits. So L'Hopital's rule, we'll have a way that we can kind of invoke L'Hopital's rule if we change the polar. We'll see. We'll do that in a little bit. Great question, though. So everyone remember L'Hopital's rule? Did you get 0 over 0, the indeterminate form, or infinity over infinity? You can take the derivative of the numerator, the derivative of the denominator, and reapply the limit. So the concept there, you're thinking about two functions. If the ratio of functions, if it's indeterminate, you can look at the ratio of tangent lines. If the tangent line is the best approximation to a function, then you should be able to analyze the limit of a quotient by looking at the limit of tangent lines. That's the idea. And so, yeah, we will see a version of L'Hopital's, but we can't just use it straight up. Why? Well, what's the derivative of x times y?
With respect to what?
Yeah, with respect to what? Right? You have a surface. There's two different directions. We're going to see that there's an infinite number of directional derivatives. You know, a derivative in one variable calculus means rate of change. And so if we're imagining a surface and you're standing on your surface, there's 360 degrees, the rate of change in each direction is ostensibly different. So we have an infinite number of derivatives. We'll call them directional derivatives. So in any direction. Now, if all directional derivatives are the same, that's a certain case. Certain case.
Line.
We'll talk about it when we get there. If you imagine a cone, directional derivative, if you're standing on the tip of a cone, it could be negative in all directions, right? So not necessarily a line.
Okay, keep doing circles.
Circles, spinning, pirouettes. All right, so, oh no, we need a break before we talk about this stuff. Let's take our 10-minute break. Let's take our 10-minute break. Because we're very... All right, let's talk about, how many of you have taken a set theory class? Oh, none of you. Philosophy class? It's a little bit like philosophy dealing with sets. So in the philosophy, the if, P, then Q type of business. So there's some of that going on here. There's some if, then, else, if, then, or programming, if, then, else. Some of that kind of logic here. So we're going to be dealing with sets, and we need to define a couple of ideas. We need to define what we mean by a point that is interior to set, and a point that is exterior to a set, and a point that is a boundary point for a set. So we're talking about a set of ordered pairs in two-dimensional space. So this region R, this cloud, the pink cloud there, that's representing a set in two-dimensional space. And point P is going to be an interior point. So when we talk about an interior point, we mean a point that has some neighborhood, and by neighborhood in two-dimensional space we mean disk. So we mean there's some open disk centered at P that's totally contained in R. Let's talk about that a few times.
Yeah.
So, an interior point, it's kind of what you think of intuitively. An interior point, if we're thinking about an interval, let's go to intervals because we are very familiar with intervals. So an interior point for an interval, if we have some open interval, say from 1 to 3, a point is interior, like 2 is an interior point, because there's going to be a little open interval around it that's totally contained in the interval 1 to 3. So 2 is an interior point. This point right here, 1.5, that's an interior point to that interval because there's a tiny little interval containing it that's totally inside our interval 1 to 3. All right, so let's get down to the nitty gritty. What we get way down close to that endpoint. the whole bizarre characterization of the real numbers, there's always an infinite number in between any two numbers, that kind of thing. No matter how close you get to 1, there's always going to be a super tiny open interval around that number that's totally contained in 1, 3. Right? So as long as you're to the right of 1, you're dealing with interior points, because every single number to the right of 1 will have a tiny little open interval that's contained in the interval 1 to 3. Yeah?
So in this concept, the endpoints are not allowed to be considered in the interior.
They're excluded, yes. So 1 and 3 in this case are going to be defined as boundary points. So we have 3 concepts that are mutually exclusive, I believe, unless we create a weird example. You have a point. A point is either interior, boundary, or exterior. So a point is either going to be, it's going to be an interior point if there's a neighborhood of it totally contained in the set. It's going to be an exterior point if there's a neighborhood totally outside of the set. And it's going to be a boundary point if every neighborhood, no matter how small you make it, contains points in and out of the set. So 1 is a boundary point and 3 is a boundary point because no matter how small you choose an interval around 3, it's going to contain points in the interval and points not in the interval. So that will be a boundary point if every neighborhood contains both.
In this case, is the set just this function that's describing our set?
So yeah, right here I'm dealing with the interval, the open interval from 1 to 3. So the open interval 1 to 3, and so a point is either interior, exterior, or on the boundary for that set as a subset of the real line.
But for like 19 there, you've got that.
Oh, we're not even looking at 19 right now.
Oh, okay.
Yeah, 19 is we're talking about stuff before we even get to that limit. Yeah.
Okay.
Now on that one this is a point, not an interval.
Right.
Right. Okay.
Perfect.
Okay, so I was just talking about intervals because it's a little easier to conceptualize intervals first. So with a set in two-dimensional space, the idea is the same though. For a point to be interior, there's got to be some little open disk around it that's totally contained in the set. Obviously, there's open disks that contain points that are in the set and out of the set. But that's not what the definition of interior means. It just means there's some interval, if you zoom in far enough, some disk that's totally contained of points that are within the set R. So you always have to have sort of this set R that you're working with. Like here, our set R is this interval 1 to 3, and all the points that are greater than 1 and less than 3, they're all interior. Right? All those are interior points. Now 1 is not even in the set, but 1 is going to be a boundary point. So 1 is a boundary. And 3 is a boundary. Those are the 2 boundary points. Now even if your set was different, you'd have the same boundary points. So what about if your interval was this? So then boundary points are the same. Interior points are also the same. Right? 1 is not an interior point to that set because there is no neighborhood of 1, in other words, no interval surrounding 1 that's totally contained in this interval. Doesn't every single interval around 1 contain points that are not in that interval? 0.9. Right? 0.99999999999, right? No matter what, you draw a little interval around 1, you're going to be containing points just to the left of 1, which are not in that interval. So 1 is not interior to that interval. It is an element of the interval. It is in the interval, but it is not an interior point. It is a boundary point. So some sets contain their boundary points, or some of their boundary points, and some don't. This interval contains neither of its boundary points. This interval contains one of its boundary points. Of course, you could have 1, 3 closed, and that would contain both of its boundary points. But this interval also has the exact same interior points for all 3, the exact same boundary for all 3. Okay, so that's the kind of the idea between interior and boundary. And we will get to a definition of open and closed really soon. But we need to have these ideas first of what it means to be interior, what it means to be exterior, what it means to be on the boundary. All right, so limits at boundary points. So evaluate the following limits. So this is a boundary point because it generates an indeterminate form. And that's, often what happens when you're dealing with boundary points. Not always. And so just like in Calc 1, if you're dealing with a value that causes the function to be indeterminate, you have to do more analysis. And usually what you did was factor, cancel a common factor, something like that. There wasn't a lot of things you tried. But one thing you did certainly try lots was to see if there was a common factor. And if there was a common factor, you canceled your common factor, and then you reapplied the limit. So we cancel the common factor, we reapply the limit, and the limit of x, we're now back to one of those basic limits. The limit of x, as x goes to 6, is 6. So that's going to be our limit. So right here, originally we had an indeterminate form. We had 0 over 0. So we had to do further analysis. Cancel a common factor, reapply the limit.
Does that mean there's some sort of hole?
Something that's either a hole or comparable to a hole. Yeah, so with surfaces, there's often, you can think of like I know we'd have to graph it to see, but a lot of times there's a tear in the surface, kind of like an asymptote type thing. So it could be any number, could be anything like in one variable, with one variable functions, but sort of more extreme. So it's not just a hole, it's probably a tear or something. Some sort of asymptote.
Yeah, so the limit of x squared minus 3xy over x minus 3y, the limit of that is 6?
Yes.
As xy approaches 6, 2.
Yeah, because x is going to 6 and y is going to 2. So if that was a y, then that would be a 2. But it could definitely just be a hole too. You have a lot of functions that have like a bell shape where there's a hole right at the top or something. That's definitely possible. So the fact that this has a limit of 6 could be just a hole, or there could be a whole line where it's torn. We'd have to graph it to see for sure. So remember in Calc 1, you know how you can introduce holes by division, by forcing. Like let's suppose I have the function y equals x. I'm sort of thinking about this one. So if we have y equals x right there, so we'd say write this function as x. If we wanted to put a hole in it, if we wanted to force there to be a hole right there at 1, 1, what would we do? How would we convert? What would we do to this to create a hole at 1, 1?
Divide by x minus 1.
Divide and multiply by x minus 1.
Because you have to multiply by 1.
So, because we want it to reduce to the same exact function, just the x. We want it to reduce to x, but we want to exclude 1 from the domain, so that would introduce a hole at 1. And so this here, they multiplied top and bottom by x minus 3y. So to me, if you think about the function f of x comma y equals x, that's going to be a plane, a tilted plane. And then this is a line, so they took a tilted plane and then ripped out a line, is what they did there. Okay. So let's go on down here. So same idea, we're looking at boundary points, or creating these indeterminate forms. So we have to do more work. So we carry the limit symbol down. We factor this. Looks like it will factor into something. That's not right. That's not how it factors.
So you have a difference of 2 squares?
That's what I was thinking it was, is it? So is
Looks
it,
like it would be.
yeah, let's try it. Let's be fancy and see if we can make that work. Is that really going to work?
No.
Is it a no or a yes? No, that doesn't work, does it? No, that's not a difference of squares.
What about
Wouldn't it
2x
be
plus or minus something?
2x minus 3y times
Oh, it
x
just
plus y?
factors like normal.
Silly idea.
Hey, yes. Let's not be fancy. Let's just do this.
But it worked the other way. If you pulled out the root 2 and the root 3, you could cancel out the x plus y.
So it did work if we were persistent.
Yeah, because it had root 2 and root 3 in both parts, so you could pull it out from the
So
top anyway.
this is easier though, right?
Yeah.
Yeah.
If we just factor, oh, that should be a 3y.
Yeah.
If we just factor it like we have learned in 3rd grade,
I think it was a bit farther along in third grade.
or 25, our 3rd decades. So yeah, that's how it factors, right? Yeah, that's a little simpler than trying to force it to be a difference in squares. Or a perfect square trinomial. Okay, so there the x plus y's cancel. And we're left with the limit of 2x minus 3y. So we then go back to our point at which we're taking the limit at. So the limit at -1, 1. So we get -5.
Yes.
Yay. So, not too crazy. You know how to plug in values, yes. Winning.
The small victories.
Small victories. All right, so here we plug in the 1 and the 2. We get 0 over 0, no good. What do you think we're going to do?
Multiply with conjugates.
I feel some.
What's that?
Multiply with conjugates.
Yeah, good. Yeah, what Hung said. Hung said,
Is it a conjugate? Yes.
multiply by the conjugate. So this is one of those cases. In algebra, they always say rationalize the denominator, but in calculus, we see lots of times it's more helpful to rationalize the numerator, this being one of them. So this will be limit. And when we multiply that out, the inner and the outer cancel. We end up with y minus the quantity x plus 1. And down below, usually whenever you do this conjugate thing, 99% of the time you do not want to combine factors in the denominator. You want to leave, you want to be patient. And what we see is that the numerator matches that first factor. When we distribute the minus sign, that whole thing is going to cancel with that thing. So we have a 1 in the numerator. And then we plug in our values, so y is going to be a 2 and x is going to be a 1. So y is 2, x is 1. So that's going to be 1 divided by square root of 2.
How did you get the 2 on the top?
Because y is going to 2. So y, so the limit of y is, y goes to 2 is 2.
Where'd you get the y?
Because the limit is.
Oh, I didn't cross up. Oh, yeah.
Oh.
Thank you. Yes.
I was so confused. What?
Yes.
New math.
New math, that's new math. That's worse than new math.
New math.
I need to do this. The
There
whole
you
thing, there we
go.
go. The whole thing gets,
It's like,
I even said the numerator becomes a 1.
yeah, you said that. That's what I was so confused.
And so now we're going to have 2 root 2 at the bottom.
Are you thinking what I'm thinking? You're totally thinking what I'm thinking.
Yeah, so then this will be 2 root 2
What are you thinking?
in the denominator.
Nothing.
And then if we rationalize that, we could multiply top and bottom by root 2. Root 2 over 4. If we want. If we want. No. I don't care.
Oh.
That's not reducing. That's not reducing.
Okay, that wasn't horrible.
Pardon?
That wasn't horrible.
No. No, there won't be a lot of these on this.
The canceling
Okay,
ones
good.
are always.
All right, so let's get to this crazy business then. So a region is open. So this is a definition. So a region or a set is open if it consists entirely of interior points. So that this gets at what you've sort of, the terminology you've used all along. Haven't you called this an open interval forever? Right? That's an open interval. this is a closed interval, this is a partially open interval, whoops, or sometimes a partially closed interval, you can say either. So that's why we call it an open interval. It's an open interval because all of its points are interior. Okay, so a region is open if it consists entirely of interior points, and a region is closed if it contains all of its boundary points. Now, sometimes that inclusion of boundary points is a little abstract. Like if we consider the entire real line as a subset of itself, that is a closed subset of itself.
So pretty much if we kind of treat infinity as a I don't know, hold on, I'm looking at one of the ones back there.
So would you think, does the real line have any boundary points?
Not really.
No. So for it to be closed, it has to include its boundary points, but because it doesn't have any boundary points, by default we say that it does include them because there's none to include, so we say that it's closed because it includes its non-existent boundary.
Alright, so
includes
infinity.
So the real line, so a boundary point, when we have the whole real line, a boundary point will be a point that has every neighborhood, every subinterval containing it, containing points in it and out of it. But are there any points outside of the real line? No. If that's our ambient set, if we're not considering the complex numbers, if the ambient set is the real numbers, and then we say, well, is the set of real numbers open or closed? Then we ask, what are the boundary points? There are no boundary points. So it's open, certainly, because every single point has a neighborhood that's contained in the real numbers. For it to be closed, it has to include its boundary. But there is no boundary, so by default it is closed.
Wait, what? You just switched up your.
Yeah, that's.
You switched your.
So it's open and closed.
Oh. It's both.
Some might call it clopen.
Never invented new awards.
Not half open, half closed. That's totally different.
So that's Schrodinger's limit
in real life,
right there.
would it be like a door half slamming in my face?
Yeah,
Door
maybe.
slamming.
But if a region is open because it only contains a certain amount of points, then the extremities of the points it contains are its boundary points, right? So anything that's open is actually closed because it has boundaries.
Oh
So,
my gosh.
But this interval right here, this interval right here is open but not closed, right? Because this
Okay.
interval does not contain its boundary. So we're looking at 1, 3, and we're doing this thing. That set right there is open because every point in it is interior to it.
So
But it is not closed because it doesn't contain 1 and 3. And if we look at 1, 3 where we close it at each of those, that set is closed. That is not open though.
So the corresponding,
The complement?
no, like the corresponding closed interval then would be like including the limit
Empty set?
to 1 on the right and the limit to 3 on the left, or is that not allowed?
Yeah, we're not even thinking about limits here. We're just
No?
either, so a point is either interior, exterior, or boundary. It's only got 3 choices, they're mutually exclusive with our examples.
Okay.
So this point right here, that's a boundary point, that's a boundary point. This set doesn't include its boundary, so it's definitely not closed.
I get what you're saying,
Okay.
but like
Oh, good.
the point closest to the non-included point is still a boundary, right?
No. Because there is no point closest to 1 that's in the set,
All right.
right? You give me a point, and I'll give you a point that's even closer to 1 that's on the right of 1.
That's fair.
Right? Right? That's the weird thing about the real numbers
You
is that
convinced me.
you pick any point, I can pick something closer to 1.
Okay.
So there is no boundary point other than 1 on the left side there. Yeah, yeah. Diana?
So is that always true for like infinity to like negative, positive infinity then?
Yes. Yeah, so if we take the entire set, it's both open and closed. So you can take a proper subset when you don't have that issue. So if you take a proper subset, so we took a kind of a trivial subset because we took the whole thing.
Yeah.
then that set's both open and closed. All right, so let's take a look at some of these guys here. So is this open, is this closed, or is it neither? Right, you could, these guys, this one right here,
No, I'm like scared.
when you do this,
I thought there were two choices.
this, no, there's not just, so, no, there's more than two choices. If something is not open, it doesn't mean it's closed.
What?
There's an else.
What? Give me an example. Is that open?
Yes.
How can something?
That's not open.
It's clopen.
Why?
It's not clopen either.
Why not?
Because clopen means it's open and closed.
Well, it's closed on the beginning and then open at the end.
This set, for this to be open, it has to, every single point has to be interior, but one is included, but it's not interior.
So that's just nothing.
Okay.
What?
Who said that? Who used the word that? It's not nothing.
What is it?
It's not open.
Okay. Draw me a shape that has
Or
that property,
not
please.
closed. But
Well,
it's
it's both of those options.
Yes.
Either of those.
It's either of
Okay.
those options.
Okay.
It's like one of those.
So it's not closed.
No.
It's like an and in there.
You're
Yeah.
right on E on A, B, C, D, choice.
I have a question. Can you please draw some kind of shape that has that open and closed property? Because that does not make sense. It's got to be one or the
The
other.
clopen property?
You said it wasn't closed.
explain
Wait, you just
what
said
my
it wasn't.
Yeah, I will. We'll do an
Yeah.
example. We'll do an example.
You just said it wasn't. You said it wasn't closed.
That one is not clopen.
Yeah.
Then
He
what
said
is that?
he wants it's not open or not closed.
Oh.
But it's
But
not
it's not the opposite of what you said.
clopen because clopen means that it's both at the same time open and closed.
So we
It's
have
neither.
5 total
Right.
options.
But it's not one of them.
Right.
I quit.
I get it.
So this is none of the above.
I get
This is
it.
none of
I
the above.
understand.
This interval here is not open and it's not closed.
So it's
None of the
neither.
above.
It's neither.
Fun
It's
to-
neither open nor closed.
I get it. I get it. Okay.
Yeah.
Opposed?
Like not clopen
Just
or
like
something?
Starbucks.
Opposed.
Opposed. I don't know about that.
Omar?
I'm opposed to that term.
So we have 5 options. Open, closed, not open, not closed, clopen. And I think we should
Noda.
introduce
Those
opposed.
4.
Noda.
All those opposed?
Above. Noda.
Okay, so does everybody agree that this is not open? Super important to understand that. It's not open.
Yeah.
So for a set to be open, every point has to be interior. And that point right there is part of the set. That's part of the set because we have a bracket, but it's not interior to the set because every neighborhood of it contains points that are in and out of the set. So it's a boundary point, it's not an interior point. So it's included in the set, but it's not an interior point.
But it doesn't contain 3.
And it does not contain 3.
So that means it can't be closed.
That's right, because 3 is a boundary point, and that boundary point is excluded from the subset, so it's not closed.
Neither. Right.
Neither open nor closed.
Okay.
Noda.
So how about that interval right there, negative 4 to 8?
Open.
Open. All right, that's open. That one? Closed, because it includes, it has 2 boundary points, and so it includes both of them. Now, before we go on to the next one, let's look at something called the complement. Complement. So we have an ambient space, in this case the real line, and we're choosing a subset. The complement of that subset is everything else. So the complementary set there is going to be minus infinity to -4 union. No, that's it. Oh no, that's an 8. Union, that's not infinity. 8 to positive infinity.
Isn't that supposed to be complement with an E?
Maybe.
I mean, unless you're saying, oh, you're looking good today, Mr. Interval, or something like that.
I can't remember how compliment is spelled. Somebody look it up.
You're looking good, Mr. Interval.
Compliment. What a nice interval.
I love your
We
smile.
don't take spelling, we're in math.
Okay, I know. It's tough. Two things at once is hard. Okay, so you told me that this is open. How about its complement? Is that open or closed?
Neither.
No. Closed. This is closed. So a set is closed if it includes its boundary points. What are the boundary points for this set?
4 and 8.
-4 and 8 are the only two boundary points. And both of those are included.
Because the boundary points on the other sides aren't defined.
There aren't boundary points out there. It goes on forever. There's no boundaries.
Aren't those closed then?
But what?
Doesn't make
Okay,
you do
infinity
It's not a boundary.
right, it's not a boundary, but infinity can be expressed as a number, right?
No.
What do you mean? No.
You can't turn it on its side and call it 8.
Fair.
There is no number. There's no boundary. So, yeah.
So is a complement in that 2D surface we were talking about, like the outside of
Yes.
the disk forever and ever and ever?
Yes. Yes.
Okay.
Exactly.
Wonderful.
Yeah. Hard to draw.
Will the complement always be the opposite of the
Yes.
interval?
So that's another way to define open. You could say set is open if its complement is closed.
Ooh.
A set is closed if its complement is open. Absolutely. That will be a secondary way to think about it. Okay, so this is closed, and its complement is going to be negative infinity to -2 union 5 to infinity.
Oh, this is interesting.
All right, and isn't that open?
Yeah.
So by definition, this is open. Every single point in that set is interior to that set because every point has a neighborhood totally contained in that subset. All right, so now we just sort of alluded to this. This one here, 3 to infinity.
Noda. None of the above.
It's open.
Oh.
Not Noda yet. We're, Noda, we can maybe go down here with Noda.
Wait, what?
Neither.
Open.
How can infinity be a boundary and?
It's not a boundary.
Well, like you said that it's like if since there's no boundary to it, it can be closed with infinity, but it's
Now it's
also
open.
not.
Okay.
Like
Okay.
it's
Okay.
possible.
So here, when we have the open on the 3, so we say that this is an open interval because every number in that interval.
Well, I got the 3. I just don't get the infinity part.
Oh, that's the harder part.
Yeah.
But think about it this way. So we're moving towards infinity. If every single point has a neighborhood contained in the subset, then that point is an interior point, right? So as we're moving towards infinity, infinity is not a point, right? We just keep on going. So if you look at 1 million and then 10 million and then 100 million, all those points are interior because they have neighborhoods that are contained in the subset,
Okay.
right? So we never get to a point that is a boundary point. So as we move towards infinity, it's like, oh, another interior point. You're included, you're included, you're included. Right? Very inclusive as we go towards infinity. Every point is included. So the complement here looks like this, and is that open or closed? That's going to be closed because every boundary point is included. By every, I mean the one boundary point. Just the number 3, that's the only boundary point. And that's included in this subset, so therefore that subset is closed. Yeah?
So you can never have a bracket, negative infinity, comma,
No.
infinity bracket. That could never happen just because it keeps on going. Even theoretically,
Yeah, theoretically we would never do it, and mechanically we'd never do it because it's not a point. It's a concept, it's not a point. So the concept is that this interval includes everything to the left of and including 3. So it's a concept, not a number. Yeah.
You said infinity is not a boundary.
Right.
In this. Okay.
Yep. Infinity is not a boundary point.
But
all
because
the
3's
but all the points before it are.
Yeah.
Like. Okay.
Before it, yes.
Before it.
Everything to the left of 3 is included.
But I mean, like on that
Or to
side.
the right of 3 here.
Okay.
Yeah.
Okay, but just not infinity. That's why it's.
Yeah. Yeah. Grant?
Is there a handy little symbol for notating the complement or no?
Yeah, I see. So a lot of times they'll just put a little C up like that, and that'll be the complement of interval I. Good question.
So just because 3's included, it's closed.
Mm-hmm. Yep. Okay, so this interval then here clearly is closed. And then this
Is neat.
nota. Neither open nor
How
closed.
do you spell no?
That's a good question. So this is not open and not closed.
Oh, they're a package deal, they're not separate.
Philosophical.
No, you could say either one. Either one. It's totally fine.
But like, they're not each individual, like,
Right.
this is not open,
They are not mutually exclusive.
okay.
Can you just make up one word for that?
So if it's not, yeah.
Like nothing.
Yeah, what would,
Oh, like non.
how do you want to spell it?
N-O-T-A, none of the above.
Exactly.
Okay, Noda.
faster.
I like this.
Okay, so with this example in particular, it's not open and it's not closed. So let's say you took that to, some 2D or 3D thing. How do you what is that?
So in a
even
2D or 3D thing, it would be you would include some of the boundary but not all of it. So you might have a disk where you include the upper semicircle but not the lower semicircle,
Okay.
right? So an example in two-dimensional space would be a simple example would be something like that, where we have a disk and we're including everything inside the disk, but we're only going to include half the boundary or part of the boundary,
Okay.
right?
That helps.
Yeah, so that would be a not open or not closed or NOTA.
What's the complement
Yeah, I
say?
was looking
Is
at
it
this
negative
now.
infinity to 8, but
So
not including?
so I see here the complement is going to be negative infinity to negative 1, excluding negative 1 union bracket 6 to infinity.
And it's complementary.
And so this is also not open or closed. This is NOTA also because that point right there is
It does have
not included, so it's not closed. This point is a boundary point that is included, so it's not open.
What about the one before that? So it would be negative infinity to 8, not including 8?
Yes. So the complement here is going to be negative infinity to 8, like that. And that's open.
So if you have a boundary or whatever that's NOTA and its complement is also going to be NOTA?
Yes.
Okay.
Yeah, that's going to be true. All right, so now that you are so good at this, let's make it hard. Okay. We're going to spend just a few minutes on this.
Yeah, sure.
If there are any tears, we're stopping. If there's any banging of head on desks, we'll stop. All right, we'll see what happens.
some
Okay.
abstract example.
So an abstract example, just to test, just test. Like Weihart likes to say, math, you make up some rules and see what happens. All right. So instead of our ambient space being the real lines, which is 99% of what you've always done is sort of had this backdrop that you're in the real line. So 99% of the time, if somebody says, if you imagine a neighborhood of a point here, so you're imagining a neighborhood of, say, 4, you're imagining points that are right to the right of 4 and right to the left of 4, correct? You're imagining all those rational and irrational numbers out there? Let's make sure that this is dotted, though. Okay, so that's a neighborhood of 4. So now if the ambient space is the real line, and let's consider this subset here. So here's our subset that we're going to be playing with, and we're going to be asking questions about this subset A. So if we were dealing with the real line as our ambient space, and not just the set of integers, if we're dealing with the real line, would 3 be a boundary point for this set?
What does the brackets mean?
It's just a collection of 2 numbers.
But is
Singleton numbers. Singleton numbers.
So if
Yeah.
it's a set, then I would include them, right?
So would 3, so if I drew this little circle around 3 and we're using the real line, does this include numbers that are inside and outside of this set?
Yes.
Yeah.
Yes, because that set is just containing 2 numbers, the singleton 3, the singleton 5. So if I draw a neighborhood of 3, it's containing points in and out. So this would be considered a boundary point for this set because every neighborhood's containing points in and out of the set. Grant?
I'm very confused.
Is that what that expression means?
Yes.
Very.
So if we're looking at the real line and we consider this as a subset, not an interval, it's just a subset. An interval is one subset, one type of subset. Right? You can have a discrete subset or you can have a continuous subset. Doesn't matter, right? 3 is a subset of the real line. Do you agree? Yeah. An interval is also a subset of the real line. A set doesn't have to have an infinite number of points. It can have just a few finite points, a few discrete points.
So to me, when I look at this interval, I see 3 and 5. So to me, that means just 3 and 5. Why do you need that whole neighborhood thing around 3 and 5? That seems really extraneous to me.
Okay, so when we want to decide whether a point is interior to a subset or exterior to a subset or a boundary point, we have to take a neighborhood of each point and figure out what's going on with the neighborhood. So that's okay. So if we're looking at, so forget about this for now, a set of integers. So we're imagining this as just a subset of the real line. To figure out whether these 2 points are interior, exterior, or boundary, we have to consider neighborhoods. So technically with a line we would do an interval, but it's hard to draw an interval that I can stretch and move around right here. So we're imagining this interval around 3. You can imagine a bigger interval. So that interval contains points that are both, well, it contains that point that's in the subset and then a whole bunch of points that are not in the subset.
Okay.
Right? So if the ambient space is the real line, then I need to lock that thing. So if the ambient set is the real line, then 3 is a boundary point.
Okay.
Everybody agree with that? That no matter how small you form that neighborhood, no matter how small you zoom in, it's going to contain points that are in this subset, namely the 3, and points that are outside the subset, 3.1, 2.9. So it's a boundary point if we're using the real line as the ambient set.
So does the delta have to be defined when we're working
No.
at that?
No, it's just concept of zipping in smaller than as small as you need it to be. Ridiculously small. Yeah. Haley?
I think my confusion is just that I don't understand, like, is it just 3 and just 5?
Yep.
Or between 3 and 5?
Not between.
Okay.
If we wanted the interval, we'd have to put brackets or parentheses.
So it's just 3 and
Just
it's just
singletons.
5. Okay.
Singleton 3, singleton 5. 2 numbers. A very small subset. 2 numbers only. Yep, 2 numbers. So, with R as the backdrop, 3 and 5 are boundary points. Everybody agree? Do you agree? So that means they're not interior points. Because an interior point means there is a neighborhood that only contains points in the subset. But every neighborhood you just told me contains points outside of the subset. Right? Points outside of the number 3.
So does
3.1, 2.9.
Does that mean that in that particular thing that you gave us, there are no interior points?
Yes.
Okay.
Every point is a boundary point.
Okay.
All right. So is it open or closed?
Close.
Closed.
Right, 'cause
Exactly.
it doesn't contain.
Exactly. Yes, it is closed with the real line as the ambient space. It is closed because it only has 2 boundary points. Both points are boundary points, and it includes both those points. Yep.
And it doesn't consist of any interior.
Correct. No interior points, just boundary points. A point is interior, boundary, or exterior. Both the points it contains are boundary points. Contains both the boundary points. And if you looked at the complement would be a mess. You go negative infinity to 3, exclude, union 3, exclude 3 to 5, exclude, union 5 to infinity. That set is clearly open. It's all parentheses. Right? Okay, so now here's where, that's reasonable. Now let's make it weird. So, instead of imagining the ambient space as the real numbers, let's imagine the ambient space as just the set of integers. Just the set of integers. Okay, so we're going to consider this subset A as a subset of the integers, not as a subset of the real line. So now let's analyze it again. Let's call it a different thing. Now let's call it B equals 3, 5 as a subset of the integers. Okay, so 3 is it a boundary point, an interior point? It's got to be one or the other.
Boundary.
Okay, I hear boundary. So, and I hear interior. All right, we've got both.
It is both. No, I'm kidding.
Let's find out. Okay, so definition of an interior point. An interior point to a set is a number that has a neighborhood that only contains points in the subset. So right here, that is a neighborhood of 3 that is including 3 numbers only. The stuff in between does not count because we are only considering the backdrop of integers. All those fractions are gone. The only numbers alive are the red dots. So this set contains 3 numbers only. It contains 3, 2, and 4. 2 and 4 are not in the subset. So that doesn't tell us much yet. And we start zooming in on the 3. Can we create a neighborhood that only contains points in the subset?
No.
Yes!
Yes.
Good. Right? The other numbers in between 3 and 4 and 2 and 3 do not exist.
Oh.
Right?
So
We're-
just 3.
Just 3. So this neighborhood of 3 contains only 1 point. And the only point it contains is an element of the subset. So that tells us that this is, in fact, interior. So it all depends on the ambient space that you're working with. If you're only allowed to look at integers, you're not allowed to see fractions. You're not allowed to see decimals in between here. If you're only allowed to see integers, isn't that the only integer in this subset, in this neighborhood?
Unless you expand it.
Right? Unless you expanded it. But to be an interior point, there just has to be one neighborhood that contains only interior, only points that are in the set. So that tells us that 3 is interior,
So
and
5
5 is also going to be interior. So let's do 5, 3. Wow, that's bad English. I would never want to proceed with that English. 5 is interior also. So B is open in this context. B is open.
Is that always true? That like if you switch
If you have a discrete set and then you take a subset of your discrete set, then yes, that will always be the case. Okay, now is B closed? We can see that B is closed in one of 2 ways. Are there any boundary points to this set? Is 3 a boundary point? No!
No.
It can't be an interior point and a boundary point. It's one or the other.
They're exclusive.
They are mutually exclusive. You cannot be boundary and inside. Interior, I should say. You can't be both.
Why'd you say that earlier?
You cannot be both. You cannot be an interior point. They're mutually exclusive. Either every point is interior, boundary, or exterior.
So how is it closed?
So, because it has no boundary, by default it includes its non-existent boundary. That's one way. Or you look at the complement. What is the complement of 3, 5 in the integers?
Well, it's just that.
It's just all the rest of the integers, right?
You wrote right there. On the side.
No! No!
Wrong.
No! Because we don't have all the fractions. This has all the fractions.
Could you attack on something like make that a subset of the integers?
The complement is going to be all these, right? That is the complement. If our ambient space is just integers, the complement of 3, 5 are all integers except 3, 5. So the complement will be all the integers except 3 and 5. And then we do the same analysis we just did. We would say, oh, is 6 interior to the complement? So is 6 interior to the complement?
Yes.
It is interior to the complement, so same exact logic that we just went through. So we see that the complement is open. And if the complement is open, then we have a closed set. See, it was using dash.
You just said it was open.
It's both.
Yeah, it is. It's open and closed.
That's clopen.
So it's open! Yay! It's on the open set!
Oh my god.
So it is clopen.
Oh my god.
Question.
Did I see tears? Should we stop?
Question.
Yeah.
Who gets to make these rules?
3-year-olds.
These things
That's it.
happen long before TV, long before radio, long
think
before
we
you
should all
travel
go
more than
home
20
with
miles
you
from your
guys.
village of birth.
So back in your time?
Back when- What? I can't hear you. What? Oh.
That was terrible.
All right, so that gives you an idea of what abstract math is all about.
Wow.
You make up rules and see what happens.
And then you fail the test.
And then you fail the test and you see what the implications of that are with your career. And then it's like,
And then you cry.
is this French fry interior to the cup of fries or is it a boundary fry?
You will never know.
Don't ruin fries too.
Okay. All right, let's.
I think we should go home now.
Yeah, let's not discuss this last example.
I'm still confused.
Yeah.
You're not supposed to understand it.
I actually have a headache.
Yeah.
Is your knowledge interior, exterior, or on the boundary?
Exterior.
I'm probably on the boundary right now because we're about to go.
Clopen.
The law of the universe has been written by a madman.
Oh, it's so clopen.
Yeah.
All right,
Laws of the madman.
let's clopen things up.
So
Is
is it also closed just because the complement is also open?
Yeah.
Yeah.
A set is closed if its complement is open, or a set is closed because it includes all its boundary points.
So it's only closed because the complement is open but the complement can't be open because
The complement is open because every point in the complement is interior to the complement.
It's also.
so then the rule just doesn't apply right
But it's
there.
also closed
Yes, it
because it
does.
includes all its
No, I
boundary
mean, the
points
rule
because there's
is
no
non-existent boundary.
So it's both. So
Yes.
if you have both in your complement, you have both in your.
Yeah. The complement of a clopen set is clopen.
Great.
Yes.
If they're Noda,
Yes.
then they're Noda.
Okay, let's go on and do more math.
You need a
Less
trademark for that
philosophy.
new term.
Okay, so here everyone agree that it's a indeterminate form. We try to take that limit, we get 0 over 0. So we are here, we're trying to show that we need to do more analysis. And either the limit exists or it doesn't exist. One or the other, not both.
Two choices.
Not with limits. Two choices only, back to basics. Either it exists or it doesn't exist. So now if we want to show that it doesn't exist, we can use this two-path process. So we are imagining our domain. Our domain is in two-dimensional space, and we are trying to find the limit as we approach 0, 0, as we approach the origin. That's where we're taking the limit at. The limit at 0, 0. So let's figure out a couple of different paths and see if we can come up with two paths with different limits. Let's approach this origin. Let's approach the origin. Let's approach along the x-axis and let's approach along the y-axis. And perhaps if that doesn't work, let's approach along the line y equals x. So these are
Substitute for right side and left side.
exactly. Exactly. So in one variable case, you would look from the left, you'd look from the right and see if you got the same number, and if you didn't, then the limit didn't exist. So here we're going to look along three different paths. So if I want to look along the y-axis, I'm setting x to be 0. So we're going to be saying along x equals 0, so this is the y-axis. We're going to let x be 0. On the y-axis, x is always 0. So then this limit becomes a one variable limit, y going to 0. All the x's have gone away. So we get that. And what is that limit? Negative 1. Correct. Now let's go along y equals 0 and see if this is enough. If this is not enough, then we'll go along y equals x. Usually these three are enough. I mean, there's times where you might have to come along y equals x squared or y equals square root x, but usually these three are enough. So, plugging in y equals 0. And that's enough. So we've now found two paths with different limits. So that means that this does not exist.
Nice. That's simple.
Right? That's pretty simple.
Wow.
Capiche?
I never knew that one didn't equal
Now there's no time like the present to learn some basic facts. 1 and minus 1 are distinct. They're not equal. They're never going to be equal.
I was just looking at it, I was like, -1.
So any questions on this? So the idea is that we've got a surface, and we want to know what the limit, what the value of the, not the value of the function, but the limit of the surface. As we get closer and closer to 0, 0, do the function values get closer and closer to something? If the surface values get closer and closer to something, it shouldn't matter how you get to the origin. Every path should have the same limit if the limit's going to exist.
So if you were going to do the y equals x, you just plug in x everywhere?
Yes.
Except that it still results 0 to 0.
And that's still going to be indeterminate, is that what you just found out? So we're going to have x cubed minus x squared, x cubed plus x squared. So we have some cancellation though, right?
Oh.
You get x over x.
So you get x cubed minus x squared, you get x cubed plus x squared. You can divide out x squared. So you would end up with x minus 1 over x plus 1. And so that would actually go to minus 1 also.
Oh.
So you could get two of the same answer.
Absolutely.
So then you just
You can
have
get 5 million that are all the same, and then one that's different.
So you
I'll
just
give you an
find
example
one
like that.
counterexample.
Yeah, exactly. We just
Secondary question to the y equals x. Is there x equals y?
sure you can do that also.
Okay.
Yeah, either one.
So, by what you just said, I'm assuming you can't use this to prove a limit exists?
Yes, exactly.
Okay.
Yeah, so we can only use this method to disprove, so to show that a limit doesn't exist, because there's no way to test all paths. Right? We can't test all paths. There might be one that we missed. So this can show that a limit doesn't exist. Samantha?
How do we, if we're getting the same limits, how do we know that we've tested enough?
Because they're going to say, show that this limit does not exist.
It's not going to be like.
Oh, so you just have to like go until you find it.
Yeah, exactly. Yeah.
But
So
you-
it's going to be all reasonable things, like x equals 0, y equals 0, y equals x, maybe y equals x squared or y equals root x.
So would they, if they asked you to use the two-path test to prove that it exists, that's a trick question.
Mm-hmm. Beware.
Are you gonna try and do
No,
that?
I would never do something. Never do something. Okay, continuity, same definition that you had in Calc 1. If for a function to be continuous, it has to be defined. The limit has to exist. And the limit and the value have to be equal. So that's the standard definition of continuity from Calc 1. Function is defined, limit exists, and they're equal. So this situation, common situation is this thing where they put a hole there and that. There the limit exists, the function value's defined, but they're not equal. Everyone follow that example? That example is omnipresent. So that's the classic example where it's defined, the limit exists, but that's not true. And the other example that we see, if we have some sort of gap like that, then there, with that example, maybe I should have done that in a different color. So with this one in green, here the limit doesn't exist. The value of the function is there, and so then both those are false. That one. Okay. right, so here they're talking about continuity is defined at a point, provided the value of the function is equal to the limit. The definition of continuity applies at boundary points kind of in the same way that we do one-sided limits. If we're looking at, here's the boundary, if we want to know whether the function is continuous at this boundary point right there, we only consider paths to that point that are within the domain here. We don't talk about paths that are not inside the domain.
Like
This
stuff
is something we're not going to really deal with. It's more of a concept that if we talk about a function being continuous at a boundary point, we're talking about all paths that approach that point from within the domain. You can't go outside the domain to analyze continuity.
So these paths might be able to start at that filled-in line on the edge, but not the dashed line.
Yes, exactly. Somewhere on the inside. All right, so let's talk about continuity in Calc 1 and in here. We basically figure out where a function is continuous by looking at where it's not continuous. And usually the places where it's not continuous are because the function's not defined. Square root of a negative, division by 0. Those are usually the problem spots where we figure out where something's not continuous. So here, are there any problems? Is there any division by 0, any square rooting of a negative? No. So this is going to be continuous on all of R2. So the entire xy plane. Continuous on all of R2. And then down here, we look and we say, oh, whoops, there's a problem. So this is the set of x comma y such that x is not equal to 0 and y is not equal to plus or minus 1. So it's going to be continuous everywhere else except those places. So if we want to draw a picture of where it's continuous or not continuous, if we want to try to get an image of what's going on. So where do we have to exclude? X equals 0, that has to be excluded. Y equals 1 is a horizontal line. Y equals negative 1 is a horizontal line. So this function is continuous on all this stuff, that in there, that in there, that in there. You know, so it's continuous on those 6 sub-regions. Continuous on each of those 6 subregions, but not at those places. And now in Calc 1, you did a lot of that removable discontinuity stuff. And we're not really going to do that in this class. It's a lot more complicated with surfaces. If you have this situation in Calc 1, that's a removable discontinuity because the limit exists and it's just that it's not continuous there. But you could redefine the function and fill in that one hole pretty easily. So you can do that same kind of thing here. We won't do a lot of that, though. So let's look at this abstract example. All right. So let's first make sure we're all looking at the graph of this surface or this function. Maybe that's not great to call that a surface, but so that function. So this function has a value of 1 if you're on an axis, and it has a value of 0 if you're not on an axis. So I've tried to highlight to give you a sense of what it looks like. These other 3 quadrants back there should also be blue, right? It's 0 everywhere except on the x and y axis. So on the x and y axis, it's like just lifting up the function values 1 unit. If you lift up the x and y axis points 1 unit. So everybody can see what that function is?
Oh, because then it's like the z-axis is like coming out of the intersection of those two?
Yes, exactly.
Okay,
So the z-axis is coming straight up that way. So this would be at z equals 1 right there.
Oh, I see.
So if you're down in the xy plane, you're walking along, and as soon as you hit an axis, there's a hole. And you look up, and then there's the function value above you at a height of 1. Okay, so first off, let's analyze this question. Clearly this function at 0, 0 is not continuous, correct?
Yes.
Right? We definitely want our math to support that that's not continuous at 0, 0. Okay, so what is the value of the limit at 0, 0?
It doesn't exist, does it?
1. It's got to be 1.
Well, no, but you could approach from within the plane, and it'd be 0 all the way up to 0, 0. But you approach from either of the axes, it's just 1 all the way. So the limits are unequal, so that has a non-existent limit.
So you're saying that along the x-axis, so when we're thinking about limits, we're thinking about along paths. So we're not, so we sort of restrict ourselves to thinking along paths like we did the right limit and the left limit. So if you're along the x-axis, so for example, our limit is what? A couple of you I think said it. But if we're along the x-axis, the y values are 0. So we're just looking at this. So if the y values, we're just coming along the x-axis, what's that limit have to be? If we're on the x-axis, all the function values are 1, right? And they're not changing. As we're moving along the x-axis here, all the function values are 1. We get closer and closer and closer to the origin, the function values are still 1. If we go over to the negative x-axis back there, all the function values are 1. So definitely the limit, if we come along an axis, along the x-axis, it's 1. Similarly, like you said, the limit as y goes to 0, so the limit, if we're going to be y goes to 0, that's also going to be 1.
We do x, y.
So this one is along the y-axis. This one is along the x-axis.
So it says up at the top along the x-axis too.
Oh, yeah, thank you. We don't need that also. Okay, so along the y-axis, did I write that right though?
I think you did it back.
I think I did it backwards too. So if we come along the y-axis, oh no, that's right. Then we want, if we're coming along the y-axis, all the x values are 0. Oh, so we want to say, I feel like I have to convince myself. Hold on one second. Let's analyze this. So if we're coming along the y-axis, all the x values are set to 0. So we want to let y go to 0. So it should be y. So along the y-axis, it should be y going to 0. And along the x-axis, it should be x going to 0. Because on the x-axis, all the y values are 0, but we're going to let the x values get closer and closer to 0. So it should be that. But now, what if we come along y equals x?
It's 0.
0. So if we come to the origin in any other path except along an axis, the limit is 0. So any other path, limit f equals 0 if we come along y equals x. Let's just say along y equals x. So therefore, limit does not exist. Yeah. And if the limit doesn't exist, the function is not continuous. All right, let's take a break. See you on Wednesday. Wednesday, week 5, I can do it.
We're a third of the way through the semester.
Today, yeah, right now. As of today, we have just finished 1/3 of the semester.
Really? As of today?
As of today. I know! We only have 2/3 to go. The complement of 1/3 is 2/3.
That's the
2.7%. Never would have guessed.
Man.
Okay, and that's where you rotate it.